All right, Chapter 14, Waves and Energy Transfer. We are really starting to move away from what we can consider um, energy and motion and velocity and mass and all those things that kind of, when we lump them together, is kind of are called Newtonian mechanics. And what we are focused on is we're going to kind of spend the rest of the year talking about wave properties and energy and how energy is distributed. So we're going to talk about sound, we'll talk about light, electricity, and if we have time, if we don't have 94 more snow days, we'll talk about magnetism. So the first thing that we're going to talk about are wave properties. And waves, there are three types of waves. Three types of waves. The first is a mechanical wave, and a mechanical wave requires a material, a medium. What is a medium? A medium is really a substance. All right. What a wave can flow through. So it has to be something. So a medium is something, air. For example, a medium, a vacuum, if a vacuum such as outer space is no medium at all because there's nothing in outer space. So mechanical waves require a medium. Water, sound, all of those mechanical waves. Sound, for example, if I try and talk in outer space in a vacuum, sound cannot travel in outer space because there's no medium in outer space. There's nothing for it to travel through in a vacuum. So that's number one. Number two, electromagnetic waves. No medium required. So this is the 7 types of electromagnetic radiation that you've studied before. X-rays, gamma rays, microwaves, radio waves, ultraviolet light, infrared, visible light. All those are the electromagnetic waves. And then we have matter waves, which are particles moving like waves, and an example of those are electrons. When we talk about how waves are produced, it typically results in a disturbance that travels throughout the medium. So if you consider a mechanical wave, I throw a rock in a pond, what happens is the water ripples out. That's a kind of a wave pulse, a disturbance that caused that throughout the medium. A traveling wave, then, is a series of pulses at regular intervals. So if I kept throwing a rock in the pond at the same exact time, that would be kind of a poor example of what a traveling wave is, but that would be a traveling wave. So 3 types of waves: mechanical, electromagnetic, and matter. What are the 3 types of mechanical waves? We have transverse waves. And transverse waves are particles vibrate at right angles. So for example, if my waves are traveling across the screen like this, left to right, my particle is going to move up and down like that. It's going to move in this direction. So what is that wave going to look like? All right, up and down. That is a transverse wave. The second type of wave we have is a longitudinal wave. And a longitudinal wave are the particles move parallel with that direction. An example of a longitudinal wave is a sound wave. So we take the same example here. The wave is moving in this direction, but now this time, instead of going kind of on the y plane, we're going to stay on the same axis. Right, so we're going to stay on the same axis. And I'll kind of show you an example of what that'll look like in class with a spring. And then what we have is we have a surface wave, which is a mixture of transverse and longitudinal. So a mixture of transverse and longitudinal. We're going to kind of try and blend them together. I'm going to try my best to blend them together. Didn't do really good there. But tomorrow in class I'll show you an example using a slinky, kind of how that looks. So surface waves, transverse waves, and longitudinal waves. The 3 types of waves. When we measure a wave, what are we measuring? We're really going to measure 3 things. We can figure out the velocity of a wave. And remember, velocity is equal to distance divided by time, but those 2 numbers are different. Those 2 philosophies are different when we talk about mechanical waves. Mechanical waves, time. we measure it with a period, capital T. That's the shortest time interval for which a wave repeats itself. Units are in seconds. So again, if I have my line here, if it takes 1 second for one wave to go, that's the period. Another second there, another second there. How much time does it take to complete one cycle? Frequency is the number of vibrations per second mixed at a fixed interval. It's measured in hertz. And how do we figure out frequency? It's 1 divided by t. And wavelength. Wavelength is the shortest distance between where the wave repeats itself. So on every line up top here, here's one wave, there's another, there's another. If I measure that distance, that is the wavelength. When we talk about wavelength, a lot of times we'll talk about our unit is our base unit is always meters. But remember, when we talk about color, it's usually going to be in nanometers. 1 nanometer is 1.0 times 10 to the negative 9 meters. Just something to keep in mind when you were talking wavelength. We use meters or nanometers. You want to make sure your base unit is in meters. So frequency is 1 divided by period. Period's the amount of time it takes for the wave to go through. One time. So how do we figure out velocity of a wave? Velocity of wave is equal to the wavelength times the frequency. So if we look at the example, a sound wave with a frequency of 262 hertz has a wavelength of 1.29 meters. What is the velocity of the wave? Well, it tells us our frequency is 262. Our wavelength was given in meters at 1.29. Velocity is equal to wavelength times frequency. It's equal to 262 times 1.29. Get those together using sig figs. Velocity is 337 meters per second. Since we're talking about waves, let's real quick review a couple things here about waves that you should know, but might not remember. So if we have crest, if I draw down below here, here's my straight line, and now I have the crest in blue is the top part of the wave. The trough in black is the bottom part of the wave. Amplitude is the maximum displacement from the equilibrium. The amplitude, I will go in green, and the amplitude is not the height of the whole wave. It's really height of half the wave. That's the amplitude, and this is the amplitude. Do not tell me the amplitude is the whole thing, because that's only the displacement from the medium, or the equilibrium height, and the equilibrium height is our red line. So crest is the top of the wave, trough is the bottom, amplitude's kind of the energy from equilibrium, not considered the height of the wave. We will continue talking more about waves as we go through, but that